Right, so what we want to do now, like I said, is start off by finishing off yesterday's lecture. And we're going to miss out about 5 slides, which I think I did last year as well, on something called the common ion effect. You're going to come back to this in 191 if you do 191. If you're not going to do 191, it probably doesn't matter for your life in general. But what I do want to do is come back to this bit, because this is something that may well be in your test. It's the sort of thing we ask you questions about. And again, it's something that you do at school, although, again, a little bit differently. Well, not differently, but with different language. And indeed, this is something I've heard anecdotally from students from their teachers, that teachers have no idea about this. So let's just do this, and then we'll move on to today's lecture. So, yesterday we were talking about KSP. We were talking about this idea that you can have some ionic compounds which, when you put them in water, only dissolve a little bit, and you form an equilibrium. And the equilibrium constant, which describes that equilibrium, is called the solubility product and is given the symbol KSP. Right? And so we saw at the end of yesterday how there's a couple of different types of equilibria that you can have. If on the one hand, something like silver chloride, which dissolves to give one lot of silver and one lot of chloride, and so we end up with this relationship that the KSP equals S squared, the square of the solubility, where that corresponds to the concentrations of the ions in the solution. And then we also saw you can have a situation for something like silver carbonate, silver carbonate we did, where when it dissolves you get 2 lots of silver ions and only 1 lot of carbonates. And so then the math works out a little bit different, and you end up with this relationship that the KSP is equal to 4s cubed, right? And then I said there's other options as well, but those are the 2 that you need to know. So depending on what sort of ionic solid you're starting with, you can have either of these 2 relationships apply, right? And so what we did yesterday then was we were looking at the situation where you take a solid and you put it in water and you see what happens in terms of how much of the ions dissolve. This last situation is kind of the opposite way round. What we want to think about now, and this is kind of what you did in the lab yesterday, is if you take 2 solutions, one which contains an ion and the other which contains a different ion, and you mix them together, will you form a precipitate of a sparingly soluble compound? Right? So, the question might go like this. If you have a solution of 0.023 mole per litre silver nitrate, and you mix it with a solution of 0.011 moles per litre sodium chloride, will you form a precipitate of silver chloride or not? Right? Because it won't always happen. Even though you've got silver ions and chloride ions there, you won't necessarily get a precipitate. But it's oftentimes useful to you to know if you will. Right? So, how do we go about doing this? If we want to work this out, then what we're going to do is we're going to work out a QSP. Right? Yesterday we talked about Ks and Qs, and we said that if you have a reaction at equilibrium which can be described by the K, and then you perturb it, then at the instant you perturb it, you can describe the reaction mixture in terms of a Q, the reaction quotient. And so we're going to do the same thing here. And so we're going to consider our reaction mixture at the moment that we mix our solutions together, and we're going to work out a QSP. Now, in NCEA at school, this is called the IP, the ionic product. But here, this is called the QSP. And what is very important to remember is that the QSP, which is related to the KSP, describe this equilibrium, even though this is not the way around you're doing the reaction in this particular case, right? This has got the silver chloride as being the reactant and the ions as being the products. Whereas in the reaction we're talking about at the moment, the ions are the reactants, and we're mixing those together to potentially make the solid as the product. Even though it's the other way around, we still have to think about the equilibrium this way, because the KSP applies to this reaction, not the one the other way around. It turns out it doesn't matter, But you need to remember that and not start trying to sort of change things around, because you'll get in trouble, right? So here's our reaction, and the KSP, which describes what you have at equilibrium, is this one, which we saw yesterday. That the KSP is just the concentration of silver ions at equilibrium times the concentration of chloride ions at equilibrium. And so it follows that the QSP will just be the same, only without those little e's, right? Because we're not at equilibrium necessarily. Now, every year when I get to this particular point in this particular lecture, I go, oh bother, I never fixed that from last year, because the next slide has a mistake in it. And so what I propose is that we're going to do it quickly on the board, since this is kind of being recorded for posterity. I better get it right. And the problem with it is that I've lost my pens. The problem with it is that, strictly speaking, this question should have the volumes of the two solutions, right? Otherwise you can't actually work it out, the answer correctly. The next slide kind of ignores that, which is bad. So let's do this properly. So let's imagine that we've got 20 mils of 0.023 moles per litre silver nitrate plus 20 mils of 0.011 moles per litre NaCl. The reasons why the volumes are important is that when we mix them together, the concentrations of each of the ions is going to change. Yes? Because you're going to dilute them when you mix the two solutions together. We happy with that? Yeah? It's like if you had 20 mils of this and you added 20 mils of water to it, then all the concentrations are going to halve because you've got double the volume. You're diluting it by adding water. Yeah? So what we want to do, on the next slide, it says what we want to do is we want to work out the QSP for our reaction at the moment that we mix those solutions together. And so to do that, we have to know what the concentrations of the silver ions are and the chloride ions are at the moment that you've mixed those solutions together. And that's not it up there, because that doesn't take into account the fact that you're diluting the solutions when you mix them together. Right? Now there's various ways that you can work out what these concentrations would be. The simplest way normally is to just, because we'll set the numbers up this way, is to notice that if we mix 20 mils of silver nitrate and 20 mils of sodium chloride, then we're doubling the volume, and so we're going to halve the concentrations of each of the species, each of the ions in our reaction mixture. Are we happy with that? Is anyone not happy with that? Right? If this was 10 and this was 8, then it would be more complicated. You'd have to do a little bit more math, but it's the same idea. Yeah? So if we have 20 and 20, then that means that our QSP, which equals the concentration of the silver ions times the concentration of the chloride ions, this number here is going to be 0.023 moles per litre divided by 2 due to that dilution. Yeah? And this one's going to be 0.011 moles per litre divided by 2. So not that, but that. And I can't do that in my head, so someone's going to have to work that out for me. Sorry?
6.32 times 10 to the 5.
Yep. Yep.
Do you divide both of them because you're adding 2 times together?
Yes. If you wanted to do it the long drawn out way, if the numbers weren't nice, like 20 mils and 20 mils, then probably the easiest thing to do is to work out the amount of silver ions in moles that you have in 20 mils of a 0.023 moles per litre solution. So you'd use that N equals C times V formula that we did 2 days ago now, maybe. Then you could work out the amount, and then you could recalculate the concentration, C equals N over V, using the new volume of 40 mils. Right? For these numbers, that would be a bit trivial, but if the volumes were not the same, if they were 12 mils and 17.5 mils, then that would probably be the easiest way to go, right? To do it in 2 steps like that. Yeah? If you're not sure about that, come and see me afterwards and I'll talk you through one on the board. Okay, so that then is going to be our QSP at the instant we mix those solutions together. Then what we do is kind of like what we did with the QK stuff yesterday. We take that value for the QSP and we compare it to the KSP, the equilibrium constant for this equilibrium, and we see if it's bigger or smaller. And so we have another couple of rules to remember, right? If the QSP that you work out is bigger than the KSP, then you get a precipitate. And if the QSP is smaller than the KSP, then you don't get a precipitate. You don't see any solid formed, right? And in fact, if you go back and look at the blue box that we did yesterday, this is the same. It's just written in a slightly different way. But if you accept that the precipitate is the reactant, then when the Q is bigger than the K, yesterday we said the position of equilibrium would move to the left. That's to the side where the solid is. So the two things are consistent. This is just worded slightly differently. Okay? And so for all of those test tube reactions you did yesterday in the lab, if you'd known what the concentrations were of all those solutions and you accurately measured out the volumes rather than just sloshing them together, then you could have done a calculation like this every time, and if we gave you the values of the KSPs, you could have predicted ahead of time whether a precipitate would have formed or not in those solutions, yeah? Just by doing this sort of calculation. Is this okay? Yeah? Okay. Right. So in this case, the Q is 6.32 times 10 to the negative 5. It's not this number, but it's still much bigger than the value of the KSP, which is 1.8 times 10 to the negative 10. And so you would expect to see a precipitate formed if you mix those two solutions together.